Now let's talk about how to find the confidence interval for a difference. This is often the case because we want to estimate the actual size of the difference. How different are these two groups? So remember, this is just the region where we expect the true value with X% confidence. So all we're saying is we want to find the region where we are X% confident that the true difference between the populations lies. So let's start by imagining we want to test a difference in gambling by sex in a survey. To survey a bunch of people and find that 24 out of 45 men gamble and that 30 out of 80 women gamble. Now I want to make a few points about why I chose these numbers. First, note that the sample sizes are different. These statistics do not require that you have identical sample sizes in your two populations. Second, despite the fact that more women in the survey than men said they gambled, we still have a higher proportion of men who gambled, because 24 is more than half of 45, whereas 30 is less than half of 80. This is important for us to keep in mind when we're doing these kind of calculations, to always be careful about what we're dividing by and what proportion we're taking out of. So if we want to calculate a 90% confidence interval, let's consider how we're going to go about it. So first we want to start by calculating our standard error. This is simply the formula that you're given above. So our p hat m, so p hat for men. So note I do put a subscript down here instead of just using a 1 and a 2 because it helps me keep track of what's going on. So 24 out of 45, 0.53. Our p hat for female or women, note that I flipped went to male, female here instead of men, women to make it a little bit easier. On the computer screen it's not so hard, but when you're writing out by hand, at least my handwriting's bad enough, M's and W's start to look a lot alike. So 30 out of 80 is 0.375. So we plug those values in. So 24 out of 45, 21 out of 45 is our Q. So that's just how many said they didn't gamble. Same with 50 out of 80. Divide by our two sample sizes. Take the square root of that whole thing, and we get 0.09198. So that is the standard error we would use for all of these calculations. Now the next thing we want to find is the Z critical value. So if we go over to StatCrunch, we're going to go Stat, Calculators, Normal, because we're still working a normal calculator. And we want to find the area that cuts off 95% of the values. So that's the case because we want a 90% confidence interval, means 5% needs to be in each tail. So here we get 1.6448536. We can Control C, we can right click, copy. Just wanted to make sure we take that whole number, all of those values, and bring them over. So if we go back here and plug in our 1.6644854, remember that our margin of error, just like it is for every one of the confidence intervals we're going to calculate in this class, is our test statistic critical value. So here is Z critical times our standard error. So 1.64 times 0.092. Note I am rounding here just to fit this on the screen. When I'm actually doing the calculation that I'm about to put up here, I used the full values. So we get 0.151. That means we need to stretch 0.151 in either direction in order to capture the true population difference most of the time. In this case, 90% of the time. This means that our confidence interval is plus or minus 1.51 from our calculated difference. So our calculated difference is this 0.533 minus 0.375. So 0.1583 is the difference between these, plus or minus our margin of error, means that we are 90% confident that the true difference between the men and women in this survey is between 0.007 and 0.3096. That is, we are 90% confident that the men prefer or are interested in gambling more than the women.